Thank you. I recently moved to Ireland, and I had a couple of great challenges there. One of my biggest challenges was to relearn how to drive on, for me, the wrong side of the road. Part of it was actually also to realize that roundabouts work a little bit differently than I thought they would. First of all, I was super scared about roundabouts when I went to Ireland, but roundabouts are actually designed for fair traffic control. They have a ton of benefits. They force traffic to slow down when entering the roundabout, so we reduce the likelihood and the severity of collisions, if you get any. This one here is my favorite one, is my favorite roundabout in Ireland. It's nearby where I work, and I believe it was in my first week, I took a wrong turn and ended up here. This was the first time I saw this roundabout. And I was really terrified because now I had this huge roundabout to drive over, and I just thought, okay, I just see this whole thing as a huge U-turn. I just drive in from one side, come back on the other side, all will be good, I'll be back on my way. Okay, so I did. I drove in carefully, I thought, okay, I'm doing good, and after about 100 degrees in, a transporter shot in at very high speed, almost hitting me. The guy was shouting, gesturing, and I said, oh, what's going on here? I have the right of way. Why is this guy so mad at me? I did not know. So the next day I thought, okay, let's try to do this again. This was super dangerous. I don't know what went wrong here. I need to find out what was wrong. And what happened was, overnight they had actually put traffic lights on the roundabout. So, but really, how could I have missed the traffic lights? Well, as I mentioned, my brain was working very hard to keep on the left lane, to drive into the incoming traffic. And as brains do when they are overloaded, they try to blend out information that you don't expect. And honestly, I did not expect to see traffic lights in a roundabout. It does not make sense. At least it did not to me. In this case, it actually makes sense. Here, this is a scalability problem. Imagine that you have this traffic stream, the green one, and you have this steady stream of traffic here. Someone coming on the red route will not be able to drive in because the roundabout is not fair anymore on the side traffic situation. In this case, it makes sense to put traffic lights to regulate the traffic here. So there are a few interesting points about this here. Roundabouts, they will fail for the targeted high traffic scenarios. Brains are actually pretty awesome. And one of the things that I found out is that we just perceive the stuff that we know and that we have experienced. So in other words, to be able to identify patterns, we need to either have experienced these patterns or we must know what we're looking for. And of course, having enough brain capacity to process it. This is actually also true for code reviews. Code reviews should be actually part of every good engineering culture. It's just a fundamental thing that we should all be doing anyway. There are a couple of good reasons for this. First of all, of course, we want to find and fix problems very early in the stage. It's also a great tool to ensure that all the good engineering practices that we should be doing are being done. And it's a great learning experience. Now I'm learning from someone telling me stuff about the code that I'm writing, saying, okay, hey Igor, what you did here, it looks good, but what happens if whatever? So I'm learning from my own mistakes, I'm learning from the mistakes of my colleagues. And one particular thing about this is sometimes you see discussions from very senior engineers in the team discussing about benefits of A over B. This is a huge learning experience. It's almost like in one-on-one or mentorship or coaching from the most senior engineers in the team, kind of almost for free, which is good. But the best reason for code reviews is because now I can find and fix everything that's causing me pain. And this is actually what this talk is about. Today, I want to talk, or I want to help us to train our brains to identify the roundabouts in our code. Basically, all the patterns that will not scale if you run a service at scale. So let's dive into this. Disclose something very quickly. What I'm doing today will be mostly C#. If we speak Java, you will have no problem to follow. The code is actually rather simple. You should not have any problems anyway. I'm not diving into any language specifications, deep dives into the language, so we should be good. Imagine we get something this in a pull request in our change set, and we want to code review this thing. The first thing that I personally do is to check for things like method names and comments to see the code intention. And if this does not match what the code is doing, this is usually a bad thing because this is a bug. I want to really rely on code documentation because it's usually more accurate than what the code is doing, and it's easier for me to follow what should be happening here. So let's do this. Here we have a method that, telling us that we're splitting on spaces. Our comment is kind of supporting this as well. And we're splitting on spaces. And tabs, line feeds, vertical tabs, new lines, next lines, and a bunch of characters that I did not even know existed. This thing looked very innocent, but now this might be a huge problem for us in production. So let's fix this one and talk a little bit about the regex itself. So regexes are usually very powerful because they allow me to express patterns in a very simple way, more or less simple, at least simpler than if I have to implement this stuff myself. Most modern languages, and this is Perl, Python, Java, C#, they implement regexes using non-deterministic finite automata plus backtracking. The NFAs are usually fine. It's just the backtracking that we have to worry about. In worst-case scenarios, backtracking are going to cause some exponential behavior. So knowing this, I wanted to compare a little bit the performance of regexes. So I have here two implementations. The first one is my regex. The second one, I'm just using the split method on a string. And by measuring this, I found out that the second one is actually 8 times faster than my regex. The question is why? Is this something that we call the Evo regex? Evo regexes are regular expressions that make excessive use of backtracking. So this is not the case here. So it's not. So are regular expressions bad things to use? Well, it really depends. So if we are executing our code at a not very high frequency, we should always opt for readability. However, if you're executing a code several thousands of times per second, now we should begin to measure. What are we seeing here? Are we running into problems with our regex or not? In a lot of cases, you might have similar performance between the regex and the stuff that you can implement yourself. In this case, you should always opt for readability. However, if your regex is expensive, you might have 3 options. The first option would be, of course, to do some horizontal scale to add more processing power to account for all the backtracking and all the processing that you'll be doing here. It's an OK option. A better option might be to revise or rewrite your regex. You can try to implement yourself. You're going to see that writing some pattern matching code is quite complex and very error prone. So we might as well try to improve our regex. We do this by trying to eliminate everything that leads to backtracking. And we try to get them as precise as possible, and we try to take things out like the quantifiers, like stars, the plus, the question mark, the conditional matchings, and the either-or constructs. So let's move on. Error codes or exceptions, which one is better? This is actually a classical question. I have seen this question many, many times. And usually in developer documentation, people are going to say, well, error codes are bad. Don't use them. Use exceptions. Because now this is forcing users to deal with problems. Well, as an engineer, I want to understand why do I have the discussion. So I measure. This code here with the exception, I'm not running through any stack calls. I'm just throwing an exception. And this one takes about 70 microseconds on my laptop on this one. This seemed to be a little bit excessive. My laptop can do around 3,000 cycles per microsecond, which means this exception here is taking me about or over 200,000 cycles on my CPU. To put this a little bit more into perspective, I executed both sides 1 million times. And what it came out to is that when I'm using my error code, I can execute this thing in about 2 milliseconds, and the regex one in about 70 seconds, which is quite a lot. So are exceptions bad? At scale, yes. So what do we do here? Exceptions are actually, they have some good pieces. First of all, they help you to understand problems. They give you, they do a walk through the call stack and give you all the information that you need to debug stuff. In reality, you don't need this information. We're not using this. We know why you're catching exceptions. We know how we're handling our errors. Why do we need to use exceptions to do this? Exceptions is to when we have something unexpected. At scale, unexpected has a slightly different definition. In most pieces, we are expecting anyway that we're having errors. And even if you have something that's completely unexpected, our next step is to create some code to handle this and make this expected. Unfortunately, we cannot eliminate our exceptions. We will be using external libraries that will be throwing exceptions, even some language constructs. And in most cases, we don't really want to rewrite the language. So what we do. In this case, we try to really understand what the problem is. It is that's happening. We try to catch the exception where they occur, and just bubble up error codes if we need them at all. A good practice is always to load test your code, especially on the error scenarios. Okay, as I mentioned, the things that happen that are unexpected at scale, they become very expected. And at scale, you're not running against probabilities, actually. You're running against real numbers that derive from these probabilities. Let me try to illustrate. If you have a code path running about 1,000 times or 10,000 times per second, and you have a probability of error of, let's say, 0.01%, you're going to run into 1 error per second, which will add up to about 86,000 per day. Well, let's look at this piece of code here. Right now, what I'm doing here, I'm doing some step and using whatever I get from the step in a second step. The question is, what happens if it fails? Even if you lower the probability for errors, at some point of time, this thing is going to fail. We don't want to corrupt data, so we might want maybe to rewrite it a little bit. Things like this. Now we check. Did we have a good response on the first step? If yes, we go for the second step. Otherwise, we roll back. The problem is, at scale, you will not always be running on your code. What do I mean? Something might come along and kill your process in the middle of execution. And this is going to happen quite often. So you have to expect that everything that happens at scale will kill your code, regardless of where you are. You won't have the possibility to handle anything in this. So what patterns can we use? We could try to use something like logs and commits. However, this is rather expensive. We should try to avoid these. I heard a few times this week about idempotent. Get operations are usually idempotent. You should also make sure that deletes and updates are idempotent in your backend. Create operations are a little bit more tricky. They are not idempotent. In this case, to make sure you're not corrupting data, it makes sense to work out of a queue. So we store a result in a queue, and if this result is available, we come with a different worker, pick it up, and work from there. Hard-coding strings is also something that's quite tricky and very error-prone, especially at scale. The main usages for strings that we care about as SREs are when they come up in things like logs, metrics, and events. And this actually, observability is a huge topic for us, and one of the main areas where we can drive a lot of improvements. And at scale, we really need to make sure that strings are consistently used. In this piece of code here, I have two types of metrics here, or actually one metric called storage operation. If we take a closer look on this one, we see that the first one has a capital O and the lower one a lowercase o. This is very easily overseen, even in a code review. The question is, what can we do better here? Why are we using the strings here? Instead, one of the things that we can do is to, instead of using strings, we use constants. In this case, I'm using enum for success and errors. Otherwise, I'm using some string constants for my error storage. This will reduce the likelihood for errors. Another example here. Imagine this one of the configuration of our alerts. What it says is if within 5 minutes we get more than 500 errors, we create a SRE ticket. That will call someone and everything will be good. The problem is we have a magic number here. Why are we saying 500 and not 400 or 42 or 2,000? Well, this might be related to the way we have measured the service, and this might increase over time. We might be better off maybe using a percentage. Let's say if 0.1% of my calls fail, I create a SRE. In this case, I might have some variations. For example, just imagine just get, let's say, 1,000 operations in a second, or 1,000 errors in a second. No, 1,000 operations in a second, and we have 1 error. In this case, again, we're triggering a call. So regardless how you define this stuff here, you're always going to run into problems in this calculation. Now, it's a way better way to focus really on what you care about. We talked a lot about things like SLIs and SLO. Make sure that you embed your SLO in your alerting as well. When you're about to breach an SLO, this is when you should be alerting, not on some random numbers. Well, this talk is a little bit too short to go over all scalability anti-patterns that we find in production. But it's actually OK. I don't want to get out of here as the absolute experts in scalability problems and all this stuff. What I want is to make you aware and maybe interested into some performance and scalability engineering. All this stuff here is highly interesting, and we could talk for hours about this. I'll be outside for this, where you can really have some good deep dives on this one. Things the time assumption, they are actually pretty awesome. They cause a lot of issues as well, as we saw with the leap second. All right, here are some takeaways here. If you can, try to pay some attention to internal implementations. We did not cover this today, but it's actually a very good practice. In most cases, you're going to find the source code of the languages you're using online somewhere. Go over your data structures. You're going to find out that a lot of them are actually not suitable for scale for various reasons. Then understand the cost of your libraries that you're using. Possibly you were using something that's adding a lot of memory, a lot of processing needs to every single request. And always make sure that you're measuring things. Measuring is extremely important, especially the error codes. And also assume that everything's going to break at any time, because this is what happens. Last but not least, to make reviews part of your culture. And I'm not only talking about code reviews, I'm talking about engineering reviews in general. So thank you very much for having me here. My name is Igor, I work for Azure. And we're open for questions, if you have any. Thanks.